Uh, it shares a lot of similarities, a lot of commonalities with ultrasound because we're going to be working in a similar range. So ultrasound is ultrasonic acoustics. Acoustic emission testing is working in those same ranges to basically analyze the sound released, energy given off by an object when it's under stress. So definitions is acoustic emissions are the generation of what's known as a transient or a short-term elastic wave produced by a sudden redistribution of stress in a material. So when you stress a material, it takes time for that stress, fractions of a second, but it does take time for that stress to move through the material. And as it does that, it can cause the release of sound. Sound in the ultrasonic range, which is what we're going to often be looking at, it often can produce sound in the audible range as well. And this can be all kinds of materials. It can be things like steels and aluminums. It can also be composites. One of the experiences I probably first had, I worked in a ski shop when I was in college. And when we'd get a new shipment of skis in, one of the first things we do, a ski, if you're not familiar with its construction, is typically wood, maybe metal, fiberglass, all kind of composited together. As we were putting skis out to put on display, the first thing we would do is take each ski, grab the tip, grab the middle, and flex it and bend it as hard as we could. And when it would do that, it would make all kinds of popping and crackling noises. And that's the stresses in that material. It's made to flex, but there are points where you kind of pop that apart a little bit. And so we would flex them before we put it on the wall, because when customers would come in, they would do that. And if they heard that crackling, they'd get freaked out. So it always did it the first time. If you do that, if you ever pick up a new pair of skis or a new snowboard or some other composite material and you're able to flex it, if someone didn't do that before, you'll hear that crackling and popping. That's a form of acoustic emission, although usually, again, the ones we're analyzing here are more in the ultrasound range, a much higher frequency. But we have to have some kind of an external stimulus, changes in pressure, load, temperature, etc. And that's going to release energy in the form of a stress wave, which will be picked up as an ultrasonic release. And the way we sense that is using, most of the time again, a piezoelectric sensor. So it's pretty much an ultrasonic transducer, but instead of sending a sound wave in and listening for it to come back, we stress the material and just listen for what sounds are being produced by it. Hence the term acoustic emission. So advantages, I mentioned, it can be used on all different kinds of material, pretty much any form of metal, any of your fiber reinforced polymer matrix, which is a fancy way of saying carbon fiber and fiberglass, even things like concrete or wood. And so it has a fast, continuous, or real-time thing. You're using, you've seen like with the ultrasonic tester, you get that feedback and that signal instantly. It can be real-time data acquisition where it's constantly doing this. It's analyzed, and it's often performed on objects that are in use rather than having to take them out of service. It can be done with indirect access, so you can have permanent or removable installations, and the sensors don't necessarily have to be right over the spot where the acoustic emission is originating. We're going to hear it as it travels through the material, and we'll look at near the end of the presentation how we can kind of figure out where damage may be occurring. And it takes minimal preparation, and in some cases, if it's permanently installed for real time, there's really no preparation. It's just the preparation's part of the construction process when the object is first built. It has some disadvantages. The first is that we're measuring a dynamic process. And so even materials that are not undergoing some kind of a failure, like the skis I was talking about, when you stress them, they'll normally give off an acoustic emission. And we don't want to confuse those normal acoustic emissions with something that is an indicator of a failure or an impending failure. And so we have to be able to sort that out. Flaws have to produce an acoustic event. Not all flaws actually do produce an acoustic event. So there are potentials for flaws that get missed with this. At this point, although it's slowly changing. This is primarily a qualitative measurement. It's more of a, is there damage present? We might be able to estimate an amount or estimate a location. And we're getting better. The technology is definitely getting better, but it's still not at a point where you can always say, there was a crack that formed at this point, and it is exactly this big. Right? We're not, it's the technology and the algorithms aren't quite there yet. However, like I said, it's gotten better and better over the years, about the last 20 years that they've been doing this. One of the things, too, we have to be aware of is this can be sensitive to extraneous noise. So we're looking at parts that are oftentimes in operation, and there are elements of normal operation that can sometimes give off similar sound waves in similar frequencies is what we're looking at. You know, so if you have sensors installed on the wing spar of an aircraft, and your engines, for instance, have a normal vibration that's in the same ultrasonic range, your sensors will pick up that vibration. We'll look at how we can filter out. There are ways to filter out extraneous noise, but if the noise occurs in the exact same range of frequencies that we have to look at, there's really no way to filter it out from a frequency standpoint. Sometimes there are ways to filter it out from an amplitude or just a signal shape standpoint. So that. If we look at how this occurs, so we have acoustic emissions that we're interested in are ultimately the result of some kind of initiation or growth of a flaw that's occurring. So it could be something like a crack, and we're very familiar with cracks. It could be something like a slip. So here you have illustration of a slip is where planes of atoms kind of slide in like a shear motion from one another. You can have dislocations. Twinning is kind of similar to slip, but in this case, you can see the bonds haven't been broken. It's just more of a bending taking place in the material. Or phase transformation. What do I mean by phase transformation? Has anyone spent a winter near a lake that freezes? Anyone ever hear the lake thunder? What's that? Pressure crack. So when water freezes and you get ice built up on a lake, if you're ever by a lake that's freezing, sometimes you'll hear these loud booms. And it's the pressure that builds in the ice all of a sudden giving loose. That's a form of acoustic emission. Okay? Or you've dropped ice cubes into your water or your pop, and it makes that popping noise, kind of that cracking popping noise. That's what's happening with a phase transformation. So it's that application or removal of a stress that results in it. And again, that could be temperature, freezing, thawing. It can be just like bending forces. It can be a bridge with a car driving over it. It can be a wing spar with the tips being lifted more than, and then the fuselage hanging down, right? Does a bending force. So it produces these elastic waves, and we learned about those with ultrasound, right? Different types of waves that travel through the part, and we're going to ultimately have detectors that are going to try to pick that up, and then we can perform an analysis of that wave as it's detected. Now, it's not just, when we're looking at acoustic emission, it's not just about is there a signal or not, or is there a wave or not, because there's a lot of noise out there. And again, there are normal acoustic emissions from something being put in operation. And so we oftentimes have to filter out, is this a normal noise? Is this normal emissions that an object is giving off? Or is it some kind of acoustic emission of interest? And so there are things we can analyze for the wave itself, the wave form, the shape that wave makes, that we can use in determining if there is an event of interest. And so some of the things we look at, so the waveform, a single useful signal, if we get a useful signal, that's known as your waveform. And these are typically transient, or they're known as a burst signal. So it's kind of a one-time thing. It's what occurs during the stress. It's not kind of the normal sound or the normal sound energy that you're seeing all the time. So ways we can look at this, we look at the amplitude, and we're saying the greatest measured voltage in a waveform, because we're often looking at these through an amplifier. We're taking that sound, running it through an amplifier, and creating an electrical signal out of it, and analyzing that electrical signal, that AC signal that's produced. So the amplitude is when you have a waveform, a single useful signal, like what's illustrated here in the lower right, there is going to be, the amplitude is during that signal event, which is, the amplitude is the highest point, or the greatest, where there's the greatest amount of burst energy. We have to decide what defines a burst signal or a transient signal. And so that's what's known as the threshold right here. And that's the minimum signal strength. So you can see on the right side of this graph, we've got some wave, some continuum waves. This would be kind of maybe the normal, noises that you hear, the normal thing. But we set a threshold and say, okay, any kind of sound energy that exceeds a certain level, minimum signal strength, that is going to be something of interest, something we want to pay attention to. The rise time is when our first peak crosses our threshold and where the actual signal peaks. So in this case, you can see here, rise time illustrated on the left, the first time that our wave crosses the threshold, up to that maximum amplitude, okay, is our rise time. So our graph here is time along the bottom, voltage or energy, strength of the signal along the y-axis. So this is very similar to what we saw in the ultrasound tester. Right? The duration is where our signal first crosses our threshold to the point where our signal no longer is crossing the threshold. And that gives us the duration of this one burst signal or this one area of interest. Counts is the number of sine waves, that signal amplitude peaks that cross our threshold. So in this case, and they've shown a couple things here. You've got your primary wave, and then you've got an absolute value wave. You can see where they take all the peaks that are below, kind of in the opposite direction. They've kind of done them in dashed lines going above. But we look at the positive peaks that cross the threshold. So in this case, there are 8 peaks. 1, 2, 3, 4, 5, 6, 7, and 8 that cross the threshold. So that's called the count, our signal count. And then if we draw a line enclosing all these peaks, that's shown here, that gives us the total energy. I think most of you have had calculus. A few might still need to take it, right? You can calculate the area under a curve, right? Everyone remember? Yeah, see? Okay, so here's an actual application of that calculus we make you take, right? So if you wanted to know the total energy, you would need to calculate the area. Now this one's a little more complex than the simple, curves that you usually do in basic calculus, but you would calculate the area underneath this line right here that encloses all the peaks, and that would give you the total energy from that burst signal, and it's known as Mars, okay? The area under that signal. So the area from this kind of looks like a little mountain range line going down to your zero line here. Okay? So that's the total energy of our signal. So there's a few things that affect that signal, what we see. And the biggest one is, our material is going to have a certain amount of attenuation, right? It's going to reduce the energy in a signal over distance. And so the intensity that's detected by our sensor is going to be directly affected by where it is in location to the source. Where did that acoustic emission originate? And so we get that occurs, and we're looking at most of our objects, right, are a 3-dimensional object. So that's going to spread through an area or a volume of material as it moves away from the source. And I've got amplitude decay for doubling a distance on a plane. So if you have a fairly flat piece of material, each time you double the distance, the energy is going to be reduced by approximately 30%. Now, it depends on the exact attenuation level of the material and that kind of thing, but on average, 30% amplitude decay for each doubling of distance. If you're in a three-dimensional structure, that becomes a 50% decay, right? Because we're spreading that energy through a larger and larger volume of material as we go further away. That signal attenuation is the result of damping. So the resistance of movement, a resistance to movement in the material, is what causes that attenuation of the signal, the reduction of the signal. The other thing we get is scattering, and that is some surfaces are rough or uneven. A lot of our composites, right, are non-homogeneous. You've got your matrix structure and your resin, right? And so not all of the sound's going to travel in a straight line away from that emission point. It's going to bounce off of things, and it's going to change direction, and it's going to exhibit refraction when it moves from one material to another, right? It'll bend the direction that sound travels. And so this is where the fact that, like I said, with current technology, can we pinpoint exactly where the failure occurred and exactly how big that flaw was? This is the kind of thing that prevents us from being able to do that with such precision, and why this tends to be more still of a, less of a measurement-based approach and more of a, we know something happened. Okay. My clicker isn't working. There we go. Some of the other things we have to be aware of is noise. There can be undesirable signals that are detected. My example earlier was oftentimes things like engines or motors are going to produce, other sounds that maybe fall in a similar frequency range to what we're looking for. You can have things like friction, loose bolts, things like wind, or air moving over the part. When you're flying in an airliner, a lot of the noise you hear is just the air moving over the fuselage, and that's going to produce ultrasonic signals. Expansion and contraction, flex points, areas that are designed to bend and move, sometimes they make noise. Things like impacts, impacts that are non-consequential. Rain, small flying objects, dust, right? That stuff's going to hit the airplane or hit the structure. And then mechanical vibration and noise, that's your other stuff like engines, leaks, cavitations, rotating bearings, anything you would expect there to be, but So to negate these, we do some different items. So one is electronic gates or filters where only specific frequencies are allowed to be picked up or are amplified. Physical distancing, physically, if we're monitoring the wing, and the engines are mounted to the tail, that's great. We'll have less transmission of that energy, or even isolation. You can put things like your vibration, your engine mounts have like rubber dampers in them and that kind of thing. And then things like electronic filtering, signal arrival time, or spectral content. Spectral content is the shape of the wave. What does the wave look like? Okay, we know what the wave shape is that the engine gives off. We can kind of ignore a wave of that shape, but we want to look for this other shape that maybe indicates some kind of a failure. So when we put this together, it looks something like this. So our general system is we're going to have sensors, and then we're going to have some kind of a signal capture and detection device, and we have to take that signal and amplify it. So we pre-amplify. We have to have a preamplifier, amplifiers, and filters, try to filter out that extraneous noise. And then we have to analyze it. And we're going to either display it, we're going to take measurements. Oftentimes it's stored or recorded. We'll look at it over time. Simplest forms are things like oscilloscopes and voltmeters. More complex ones are computers. And some of these are even now being built into the avionics on the aircraft where they can even build these sensors in place. The original application was on things like engine vibration monitoring, but more and more you're seeing structural vibration monitoring as well. I've got kind of an illustrated version of this. So it's just a little graphic on a website whenever it decides to load. Our internet being slow this morning. just a web browser. There we go. So here is a little illustration of it. So they're showing it in like a beam. You have a crack that forms that produces an acoustic emission wave. Signal gets picked up and analyzed by our acoustic emission instrument. So you can see here, there is no sound wave being put out by the transducer. So it's not like, unlike ultrasonics where we induce a sound wave and then listen for it. Here, we're going to listen for whatever ultrasonic waves are given off by the material. This is just a static version of it. So you can see we've got our acoustic source. And this is what I was talking about with a three-dimensional object. We get that attenuation, right? That energy is not just going to go towards our sensor. That energy is going to spread in all directions. Okay? And so we'll pick it up, we'll preamplify it, and we'll use our instruments. We have different ways to display it. Oftentimes, if you have real-time monitoring, it doesn't even display anything until you get some kind of an abnormal situation, and then you'll get like an alarm or an ICAS indication or something like that if it's an aircraft application. But we can detect it, measure it, record, perform interpretation evaluation. The sensors themselves look very similar to our ultrasonic testers. So if you look at this, it looks a lot like an ultrasonic probe or transducer, except these aren't a transducer, they're only a receiver. They're not going to transmit any signal. So you have a piezoelectric element. It is coupled. Now, we used a gel or a liquid couplant in ultrasound. The coupling mechanism in acoustic emission is oftentimes, if it's portable, it may be a similar gel. If it's a built-in system, it can be the epoxy or it can be used whatever material is used to bond the sensors to the structure. That's what creates that coupling, that acoustic coupling. And then same thing, you want the energy coming in from the side of interest, in this case, the bottom. The top has damping material and other stuff like that to limit the amount of vibration coming in from not the correct direction. And so our transducer converts that mechanical motion into an electrical signal that can then be analyzed by a computer shown on a display. The piezoelectric, same kind of zirconate titanate crystal. Is the same thing we use in our ultrasound transistors, and it's running in a similar frequency, 30 kilohertz to 1 megahertz. So this should be old hat by now. With these, the signal is typically preamplified. Again, these are a very, very small signal, very, very small amount of energy we're capturing. And so we need to boost it up to a point where we can actually perform analysis on it and be able to see what's going on. And so oftentimes the preamplifier, let me go to the next slide, oftentimes the amplifier and the measurement circuitry is in one location, our sensors are in a different location. And so there may be a little bit of power sent to the sensor to run a preamplifier so it can boost the signal to send it a longer distance to our actual measurement equipment, especially if you have multiple sensors along something like a wing spar or various areas of the fuselage. So the signal is captured, it's boosted by a preamplifier, that's the raw signal. A preamplifier boosts everything. We have some signals we want, some signals we don't want, we're gonna have to filter it and clean it up. But a preamplifier boosts all of that because sometimes it's so small it's hard to sort out what we want and don't want at the raw level. Then there's going to be some kind of a filter to eliminate, the most common is a frequency-based filter. So we can have frequencies that are above and or below the target frequency. And these are known as, so if it allows frequencies above a certain frequency, that's known as a high-pass filter. If we only allow frequencies below a certain range, that's known as a low-pass filter. And if you have a high and a low-pass filter together, okay, you have one filter that blocks everything below a certain point, and the other one blocks everything above, they allow the stuff in between, that's known as a band-pass filter. And it allows a certain range of frequencies to pass, to continue on, where it then goes to a main amplifier. So now we have a clean signal, and that goes to the main amplifier and the actual measurement circuitry. In practice, many of these systems have multiple sensors that feed in and can be used to show, to help find locations and that kind of thing. So you can have a system that just uses a single sensor. It's not going to tell you much more than did something occur or not. It really can't tell you where. It can't tell you how big of an event it was. It could be a small event close to the sensor, right? And that's going to produce a signal. It could be a big event far away from the sensor, but by the time the sound travels to the sensor, it may be a similar intensity to that small event close to the sensor. So if you only have a single sensor, all it really can tell you is that there was some kind of an acoustic event, but it can't tell you where it was, and it can't tell you how big it was, how big of an amplitude it was. Okay? So basic form of these used to use just a voltmeter, a voltmeter and an oscilloscope. Computer-based systems now, portable systems often they can be based on a laptop or a PC where you have kind of a general use computer where it's got a sensor interface, or they can be purpose-built specialized devices, or more and more, because the price of this stuff has come down and its usefulness, its utility has gone up, it makes sense to permanently install it and build it into the object or into the vehicle that you're going to be monitoring. And so those are fixed systems, so those are typically specialized and they're tailored to the specific application. And the advantage with those fixed systems is now we can provide real-time and continuous monitoring and indication. And this is what we're moving into. Ultimately, though, I said with a single sensor, you know that something had happened, but you don't necessarily know what or how big or that kind of thing. Really, we want to move into a point where we can start to locate the source and we can start to measure the signal. We want to get a more quantitative number. We don't just want a qualitative indication that something happened. And so to get that those more quantitative numbers, we need to start adding things like additional sensors and additional signal processing. In order we increase the sophistication of the system, and now we can start to make some of those measurements. Again, they're not perfect yet, but they're definitely getting better. Okay. Some of the things that we run into, the easiest things to do this in are those that are homogeneous and regular shapes. So homogeneous, not just the structure, but the material the structure is made out of. Most of your metals, steels and aluminums and that kind of thing are homogeneous structures, right? It's the same metal. It might be an alloy, but it doesn't have like two different things. When you get into composites, those tend to be non-homogeneous. You have some glass fibers in there. You have some plastic resin in there. You might have some honeycomb material in there. There may be all kinds of different things in a buildup that are all going to affect the sound transmission differently. And so when we're dealing with that, it becomes much, much more difficult to perform those quantitative measurements. But if we know our structure really well, if it's been studied and they've created standards and they've gone through, created basically samples and tested them, we can start to learn how does sound normally transmit through this material. And we can apply that and start to get those more quantitative measurements. So the other thing that can affect it is the shape of the material. Sound, if you have a bend in the material or you have an angle in a material, the sound's not going to transmit around it. What I mean by that is if I draw, if you have like an I-beam, right? And the flaw occurs somewhere in the web. In the web, I mean like this part here. If your sensor is off to the side, sound waves aren't going to be able to travel directly from that flaw to my sensor, right? It's got to make that corner. And so things like geometry there, a sensor here is going to pick up this flaw different than if a sensor was directly above it, or if a sensor was on the side right here, right? Compared to if we just had a rectangular or cylindrical block of material, it wouldn't matter as much where we put our sensors on it. So we've come up, the researchers, those that develop these techniques, have come up with methods in order to make these more, to gain more utility from these, to increase our ability to perform quantitative measurements. And so different ways we can arrange sensors in order to start to get that quantitative analysis. So we can have things known as linear, zonal, or even point location. So one step up from a single sensor is we can have two sensors and we can perform a linear measurement. And what this is doing is we're going to have two sensors. They're going to measure differences in the signal arrival time as well as the energy that essentially is on a straight path from one sensor to the other where a flaw occurs between them. It could even occur past them. You know, if this material was longer than our two sensors, you know, if we had a flaw that occurred on the blue block of material, if a flaw occurred to the left, that would be picked up by the left sensor first and then the right sensor. Or as shown here in the left diagram, you know, if we have an acoustic emission source that is not centered between these two, you're going to get the sound is going to reach, in this case, the left sensor before it's going to reach the right sensor. And it's going to be more intense. You're going to have more energy that reaches the left sensor than you are going to meet. That's going to reach the right sensor because there's a greater amount of material that has to travel through a greater level of attenuation. And so by analyzing those differences, now we can start to locate, you know, approximately where did this flaw occur, and potentially how big of a disruption occurred, how big of a flaw took place, how big of a crack formed, you know, or how big of a delamination took place. Okay. The next step in this process, and this is used for materials that tend to have high attenuation, is we can have a zonal system. Okay? And this can be 2D or 3D, but we have an array. And the key here is that these sensors are placed in such a manner that a flaw, say we look at sensor 4 here, by calling it zonal, a flaw that occurs in zone 4 would only be picked up by the sensor number 4. Okay, so that's zonal. Compared to the next one we'll talk about where more than one sensor would potentially pick up a flaw. But zonal relies on the fact that in all likelihood, if we get a flaw anywhere in cell number 4, the only sensor that would pick it up is sensor number 4. So no sound is going to travel further than the distance from a sensor to the edge or the corner of one of its zones. So what does that tell us? If we get a signal at sensor 4, what does it tell us? Cracks in zone 4. Does it tell us anything else? It doesn't tell us how big it was. It doesn't tell us how far it was from the sensor, other than we know it's no further than the edges of that zone. But because we're not picking it up anywhere else, we aren't going to do it. Now, it's not an ideal situation because we can't pinpoint it as well. Multiple sensors are better for pinpointing. But if you have a material with high material attenuation, where sound doesn't travel very far, it could be prohibitively expensive to install enough sensors where you could pick up that signal with more than one. You'd have to put the sensors so close together or install so many of them that it wouldn't make sense, right? It would add weight, it would add cost, it would add complexity. So there are materials where there's limits to how many sensors is it reasonable to install. And those that have high attenuation, it's not. And so now we're going to do a zonal system. So the source is assumed to be in the attenuation zone, but we can't tell where. We can't necessarily tell how big it is. If we have a low attenuation material where we know the sound's going to travel further, then we can start getting into a point location setup where we have, again, a 2D sensors set out on a plane or 3D sensors put on multiple different parts. And we would have a signal that's going to be received by multiple sensors. It could be as simple as 2 sensors receiving it. It could be more than 2 sensors that receive it. And so what happens here now is each one of these sensors is going to measure the energy. It's going to measure the difference in arrival time. And with that information, we can start to triangulate or other more complex equations that can be used to locate where a flaw occurred and estimate how big or the size of the flaw that occurred or the acoustic event that occurred. If 2 sensors are able to pick up a flaw or pick up the sound, we're able to get a roughly linear location. We can say it's somewhere along a line. Okay, that's perpendicular to the line between. So if on this left part here, you know, sensors 1 and 2 picked up something, we would have a line running perpendicular to the distance between them. Our flaw would be somewhere along that line. It's hard to determine size at that point. If we have 3 sensors that pick up a signal, then we can start to do planar determination. We can figure out where it is in a plane. But again, we may not be able to pinpoint exactly where it is in a 3D object. But if we have 4 sensors, we can start to do a volumetric determination. That is, we can determine a specific point in space. I bet a lot of you have used a similar type of setup. Probably not driving here because you do it every day, but when you take a trip. What's something that uses a similar setup to this in your everyday life? GPS. You can think of the sensors like the GPS satellites. And they can, now we're kind of going the opposite way. Those are sending signals, your GPS unit's picking it up. It would kind of be like if your car or your phone sent out a signal and the GPS satellites picked that up, they could triangulate where you are in space. And we're doing the same thing here with sound instead of with radio waves. Okay, by looking at the time and the intensity of the signal, we can figure out where it is. And so with geometrically complex parts, you can actually take that geometry and that complexity and you can build it into the equations and the algorithms that are used to determine it. Right? They're not just linear now. We can know that, you know, if a crack forms here, you know, that sound isn't going to travel a straight line to this sensor. It's going to have to travel up and over to this sensor. It's going to travel a straight line here, and it's going to travel a straight line here. So we can look at the time difference between these 3 sensors, for instance, and probably tell there's a crack here. Because a crack down here, you know, it's going to hit the sensor first. It's going to hit this one second. It's going to hit that one third. Okay. You know, if we had another sensor down here somewhere, we could, you know, you can see the more you add, the better your resolution can become. Okay. These setups can work in 2 ways. So there's what's called passive, which is illustrated at the top, and active at the bottom. So there are active acoustic emission systems as well. In a passive system, we're using what's called an independent event. Here they're saying a tool drop, but this could be wind. This can be a vehicle driving across a bridge. This can be the flex of the wings when the plane lifts off the runway. As the lift starts to form, the wings flex. We can listen for sounds in the wing spar. Okay, that's a passive thing. There isn't a specific, we're not generating a specific energy event in order to trigger an acoustic release. We just use an environmental stressor to do that. With an applied signal, we can also have a form where a controlled event, a signal, a stress is placed on the part intentionally, and then we listen for it with our sensor. It's kind of almost getting into that ultrasound thing, but the stress here is we're not listening. This isn't sending a sound wave in that we're listening for. It's inducing a stress in the material that we're listening for what the material does when it reacts to it. Okay? So keep that in mind. The big difference between ultrasound and acoustic emission, even though they work in the same range and they use similar sensors, is that in ultrasound, we put the ultrasound in the material. We listen for that same ultrasonic signal. In acoustic emission, we stress the material. The material gives off an ultrasonic signal, and we are listening for that. And we can passively do that, or we can actively stress the material as shown in the bottom. The nice part about with a controlled event, an active stress, is not only can we induce it, but when we induce it, we can send a signal to our detector to say we have induced it. And so it knows when to listen for that event. It doesn't necessarily have to be listening all the time. Or if it is listening all the time, it makes it easier to filter out any kind of extraneous signal. Okay? Versus if we're just doing a passive sensing system at the top, it always has to listen, and we have to build in filtering, whether it's frequency filtering, whether it's waveform filtering, a certain shape that we're looking for, certain wave shape we're looking for, a certain energy level, a certain Mars level that we're looking for. That it's going to be listening. It's going to have to sort that out. It's going to have to pick it out, be able to pick it out of all the noise. Okay, so there are advantages to doing active, but an active one has to be, you have to build in or create that active stimulation item. Okay. So in aerospace, what we're seeing is permanently attached sensors are becoming much more common. We're going to monitor especially hard to access structure or hard to inspect structure, or structure that's critical that we want to be able to monitor more often than the scheduled inspections that would occur in a maintenance environment, like a maintenance facility. So wing spars are a common one here. Here is a diagram of how a wing spar setup would be in a permanent install. So you have your fuselage, you have multiple sensors along the length of the wing spar. And you can see you've got lift is going to be flexing the wings, the gravity pulling down, primarily the fuselage, right, is your stressor pulling down. So that difference in stress on the wing is going to flex the wing. And if something occurs in the wing spar that causes a release of acoustic energy, you can pick it up, and you can have some idea of where it is and potentially how big of a flaw just occurred. Trunnion areas where the landing gear attaches are high stress. When do you think you would listen for a signal from a trunnion area? On touchdown, right? All of a sudden your gear goes from hanging to supporting a bunch of weight, right? That's a big stress change on the gear. You monitor that if there's any vibration. Engine mounts, you can also use it on impact detection. First aircraft or spacecraft that used impact detection was on the Space Shuttle Orbiter. Were you guys alive when Columbia crashed? 2003-ish? Do you remember that? I know, you were probably very young. Anyone remember, do you know what caused the Columbia accident? The Columbia crash? The heat shields on the leading edge of the wing? Why'd they fail? No. So on liftoff, they'd had issues with the big orange fuel tank that's part of the space shuttle on takeoff. That orange is insulating foam. That tank is cryogenic oxygen, and I can't remember what the fuel thing is, but it's a hypergolic liquid. You mix it with oxygen, it ignites on its own. But it's cryogenic. It's very cold, so that tank is insulated. That orange, the reason it's orange is the insulation's on there. Fun fact, the first 2 shuttle launches, they painted that tank white. That tank burns up. They drop it and it burns up on reentry. That was like 600 pounds of paint. They realized they didn't actually need to carry into orbit. So they stopped painting it. But anyways, the orange foam would get brittle. Pieces of it would come off. When Columbia launched, a piece of foam came off the tank and it struck the leading edge of the orbiter wing. The wings on what people call the space shuttle. And it punched a hole in that heat shield. And during reentry, the hot ionized gases were able to enter that hole, and they basically melted the support structure of one of the wings from the inside out and caused the spacecraft to become unstable and start tumbling, and it disintegrated on reentry. So after that, they noticed this on camera footage, but they had no idea how big of a hole. They couldn't inspect it. It was in a blind spot. The astronauts couldn't see. They knew something hit the wing. They saw it, hit it on video, but they had no idea what was happening. So that crew knew there was a possibility of that happening before they re-entered, and they had nothing they could do about it. They put these impact detection items on the shuttles after that. So they could monitor, and they figured out, okay, if we have something hit the wing and it causes a breach of the heat shield, this is the kind of acoustic emission that we'll see. In order to know, be able to know, is it or is it not safe for reentry? Okay. Fan blades, vibration monitoring, engine vibration. And then things like fluid flow and leakage as well. So you can listen to the sounds given off by things like hydraulic systems, fuel systems, and oxygen systems as fluid flows through. We did in systems class, we did a hydraulic system. We checked fluid flow. You remember doing that? Hooking the meter up and measuring the pump amperage, right? We didn't do that at the airline. We had more modern equipment. In order to do hydraulic system flows, we had ultrasonic sensors that we would attach to the hydraulic lines, and it would listen to the acoustic emission of the fluid flowing through the line, and it could calculate what the fluid flow was based on that. Now, that's a portable system. It wasn't always installed in the aircraft. We would put them in place, we'd perform our tests, we'd remove it, but that is a form of acoustic emission inspection used to find it basically ultimately allowed us to figure out the health of the seals in the various hydraulic actuators based on the fluid flow. So it's kind of a different application of it, but it is a form of acoustic emission. So aerospace is seeing a lot of this, and it can produce, the big key is being able to do this long-term monitoring and less invasive form of inspection. If you need to inspect the wing spar, you don't have to pull all the panels surrounding the wing spar. If you need to inspect the trunnion, you don't necessarily have to remove the entire landing gear from the trunnion in order to do an inspection of the trunnion itself. Right? You can do real-time monitoring and save that. That's it.